But what now?
So you're stuck at home and you just finished your fifth Netflix series this week. Great! Now you've got nothing better to do than learn chemistry. Here's a few things that you're going to need to start this glorious expedition of chemistry at home. You will need your periodic table, a healthy dose of hand sanitizer, your calculator, your favorite snack. Maybe you should consider a healthy one. Your dog, if you have one, and some toilet paper. On second thought, make that double.
Welcome to the first instructional portion of the first episode of Corona Chemistry, where we will be discussing percent composition, empirical versus molecular formulas, molar conversions, and one-step, two-step, and three-step stoichiometry calculations. Beginning with percent composition, it's like finding the percentage of anything. You're taking a portion of a total substance, and you are finding the percent of the mass that substance is contributing to it, right? It's just like if you have a 50-question test and you only get 35 correct, 35 over 50 times 100. Well, in question number 1 on the worksheet that you're following along with us on, the question is, what is the percent composition of each element in N2O5, dinitrogen pentoxide? Well, just as I said before, percent composition is just like percent of anything. It's what you are looking for over your total. Well, a great place to begin is what is the actual total mass of N2O5? And for you to find out what the molar mass of N2O5 is, you're going to have to take a look at your periodic table, as your periodic table has all of the molar masses of each element on there. Very, very handy, in a very handy place for you. So we've got 2 nitrogens and 5 oxygens here. You have to take into account how many nitrogens and how many oxygens there are. And so, looking at the periodic table, each nitrogen, and there's 2 of them, has a mass of 14.01, and each oxygen, there's 5 of them, has a mass of 16, which has a total mass of 108.02 grams per mole. And so that's the total mass of dinitrogen pentoxide. And this question says, what is the percent composition of each element? So we're actually going to have 2 separate answers here, a percentage for nitrogen and a percentage for oxygen. Well, if we want to find the percentage of nitrogen, let's go over here for that. You can tell I'm new at this. Percentage for nitrogen, it's going to be the mass that nitrogen is contributing to the total mass over the total. And so we're going to take the mass of our 2 nitrogens, 2 times that 14.01, over the total, which was 108.02 times 100. Something we forgot to mention at the beginning is finding percent of anything. The final step is to multiply it by 100. And so we're going to take our 2 nitrogens, the mass of each nitrogen, 14.01, divided by the total mass, 108.02, multiply that by 100, and we get our answer. Percentage of nitrogen is 25.94%. Well, the second part of this question is, what is the percentage of oxygen? Well, you could do this one of 2 ways. You could do the exact same calculation, putting the 5 oxygens times its mass of 16 over the total 108.02, or if we realize that our percentages must add up to 100 and there's only 2 elements involved, well, all we really have to do is 100 minus the percentage of nitrogen, which is 25.94%, and we're going to get our answer for oxygen, 74.06%. Looking at question number 2, what is the percent composition of sodium in sodium phosphate? Well, your first problem here is finding out what actually sodium phosphate is, because if you don't have the right formula to begin with, then you have no chance of getting the correct numerical answer in the end. And so what we have to draw back to is, how do we find out what the formula for an ionic compound is? Well, sodium, symbol Na, has a charge of +1, as it is an alkali metal, and all alkali metals have a charge of +1 in their ionic compounds. And phosphate is a polyatomic ion, or a chemistry gang, as I like to call them, PO4 with a charge of 3-. And so what I'm sure your teacher has expressed to you or taught you is the swap and drop, the flip-flop, the crisscross, as I call it. They take their charges and they switch over to the other sides. And so we end up with a formula of Na3PO4. But if you didn't get Na3PO4 to begin with, well, then you have no chance of getting the correct answer in the end. For example, the most common mistake most kids would make would be to simply smush the 2 components together 1 sodium, 1 phosphate, very incorrectly getting NaPO4, which is certainly not the formula that you're going to want to rock and roll with in this question. And so the question is, what is the percent composition of sodium? So we only care about one element here as our final answer in this question, sodium in sodium phosphate. Well, just like in the former problem, we want to find out what the total mass of sodium phosphate is. And so we have to account for how many of each element are actually present in this formula. There are 3 sodiums, 1 phosphorus, and 4 oxygens here. Well, if each sodium has a mass of 22.99, a molar mass of 22.9, and remember we're getting these values from the periodic table, and there's 1 phosphorus with a molar mass of 30.97 grams per mole, also from the periodic table, plus the 4 oxygens that each have a mass of 16, add that up into your calculator, and you're going to get right around a molar mass of 163.94 grams per mole. Give or take a few hundredths of a gram or so, as you might have different periodic tables with different values, or you might be rounding. Try to round as little as possible, but there's a little give and take here. But either way, that's our molar mass that we are very much going to need, and that is the total that we are concerned with. And so in finding what the percentage that sodium is contributing to that, we want the mass that sodium is contributing over the total mass, 163.94 grams per mole, and then multiply by 100. And so we're going to bring that over here. We have our 3 sodiums times their molar mass of 22.99, as that is the total mass that sodium is contributing. We don't want the percentage composition of just 1 sodium. We want the percent composition of all sodium in the compound. And so then we're going to divide that by the total mass, 163.94 grams per mole. You don't have to label in your work. Multiply that by 100, and if you plug that into your calculator correctly, we should get the answer as the percent of sodium is 42.07%. There aren't really significant figures to take into account here, as there's not really a numerical measured value that we are starting off with. So I always tell my students, give me a couple decimal places. You don't want to always round to the nearest whole number, as that's not going to always necessarily give you an accurate answer.
Quarantine log, day 12. I combined a canned green bean with a spicy nacho Dorito. It honestly wasn't that bad, but it was a new low. Talk to you soon.
Moving right along to our second topic of today's video, and that is going to be empirical versus molecular formulas. Well, to begin, what is the definition of each of these? Well, we first need to understand that the molecular formula is actually the true formula, what a substance actually is, whereas the empirical formula is actually the simplified version. It is the most simple ratio of the elements in a compound related to one another. For example, if we took the very common substance glucose C6H12O6, this currently has a ratio of 6 carbons to 12 hydrogens for every 6 oxygens. This is the molecular formula, the true formula of glucose. However, it is not the most simplified ratio of these substances, these elements, to one another. And so what we could do is we could reduce each of these values by a factor of 6, and we get the empirical formula as CH2O. 1 carbon for every 2 hydrogens for every 1 oxygen. Now this is the most simplified ratio of these elements to one another. And so we are going to be able to calculate and find out what the empirical formula of a mystery substance is, and then we're going to learn how to do an extra step that then finds and determines what the molecular formula of a substance is, the true formula of a substance. The question we're going to begin this topic off with reads, what is the empirical formula of a compound that is 87.40% nitrogen and 12.60% hydrogen? They typically start you off with percentages, and that's totally fine, not anything unfamiliar, because what we are going to first do is assume that whatever this mystery substance is, that we have 100 grams of it. Because if we have 100 grams of a mystery substance and 87.40% of it is nitrogen, well then we also have 87.40 grams of nitrogen. And if 12.60% of it is hydrogen, well then we also have 12.60 grams of hydrogen. Now, as it stands right now, we can't actually compare masses of one element to masses of another element, just like it is in the human world, right? You as one person weigh a certain amount of pounds, and your brother, your sister, your mother, your father might weigh a different set of different pounds, right? Produce in the grocery store. For whatever reason, bananas weigh a whole lot less than white asparagus. I don't get what all the hype about white asparagus is. I think it tastes the exact same as regular green asparagus. And yet, it's priced roughly 10 times more than a freaking pound of bananas. So here we are. We have to put them into a unit that we can relate them together as. And that is going to be the mole. The mole is the central unit of chemistry and is the universal language of chemistry. And so what we're going to do is we're going to convert our grams of nitrogen and our grams of hydrogen to moles of nitrogen and moles of hydrogen. And the way that we are going to do that is we are going to divide them by their molar masses on the periodic table. So nitrogen is going to get divided by 14.01. You can find that value on the periodic table. And hydrogen is going to get divided by 1.01. Okay? And when we get that in our calculator, we don't want to round we want to round as little as possible. You should get right around 6.24 moles of nitrogen and 12.48 moles of hydrogen. Now, as it stands, this is not a very simplistic looking formula. If I were to write this right now, it would be N 6.24 and H 12.48. And that doesn't look very good at all. In fact, it's completely incorrect for a couple of different reasons. One, it's not simplified. And two, Dalton, the father of the modern atomic theory, with his law of definite proportion, says that atoms are only going to get together in whole number ratios. And so the fact that our two values, one for nitrogen, one for hydrogen, neither of them are whole numbers, this is not going to fly. And so we're going to have to do a couple of extra steps here. Being that we want the most simple ratio of these elements to one another, what we are going to do is we're going to divide by the smallest number that we see. So once we get to this step, once we've converted to moles for each of our elements, and it doesn't matter if you've got 2 elements, 3 elements, 4 elements, 5 elements, doesn't matter. Whenever you get to this step, whatever the smallest number is, which obviously 6.24 is smaller than 12.48, we're going to divide each of our mole values by that number. So 6.24 divided by 6.24, and 12.48 divided by 6.24. Obviously, any number divided by itself is 1. Oops, we've got a card for this. So we are going to have 1 mole of nitrogen right here. And 12.48 divided by 6.24 is right around 2 moles of hydrogen. Now those are some simplistic whole numbers. And this is what our final answer is going to look at. We have 1 mole of nitrogen for every 2 moles of hydrogen. So our empirical formula for this substance is NH2. That is the empirical formula. It doesn't mean that that's what this substance actually is. Now, sometimes the empirical formula is the same thing as the molecular formula, but we might run into one of those situations a little bit later down the line. For example, if you were to look at water, H2O, it's 2 hydrogens for every 1 oxygen. You can't simplify that down anymore. And so, yes, water's chemical formula is H2O. Its empirical formula is also H2O. So NH2, the empirical formula we just determined, it could be that this is the molecular formula, whatever this unknown substance is. We just don't have enough information for that yet. And so in a couple problems from now, we're going to determine how to find out what the molecular formula of a substance actually is. Moving right along, question number 4 on your worksheet is, what is the empirical formula of a compound that is 25.94% nitrogen and 74.06% oxygen? Well, just because it's percentage doesn't mean we're going to have to do anything with it. We're going to assume that we have 100 grams of this mystery substance. Therefore, we have 25.94 grams of nitrogen and 74.06 grams of oxygen. But we cannot relate grams of one substance to grams of another substance. We already went over that with the whole asparagus conversation. And so what we are going to have to do is convert these elements to moles. And so we're going to divide each element by its appropriate molar mass. Nitrogen's molar mass is 14.01. And oxygen's molar mass is 16, roughly. 15.999 if you want to be real picky here. So either way, when we plug that into our calculator, we get 1.85 moles of nitrogen and 4.63 moles of oxygen. This shouldn't look any different from our previous procedure that we ran in the previous problem. And so now all we're going to do is we're going to take the smaller amount of moles. We're going to divide each molar value by that number itself. So we're going to divide 1.85 by 1.85. And we're going to divide 4.63 by 1.85. It should come as no surprise that this number is equal to 1. But then we run into a bit of an issue right here. 2.50 moles of oxygen. So as it stands right now, if we were to write this formula, it would be NO2.5. And as we just discussed, that does not fly, as atoms only get together in whole number ratios. That's what the law of definite proportion states. So this cannot be our final answer. It's not possible. And so we're going to have to look at one extra step. Some of you might be saying, well, what if we just round up? What if we just round down? You could, but it's going to make it very, very inaccurate in the long run. If you're taking these millions, these billions, these trillions of atoms that you're considering in the long run, it's going to make it very accurate. If you're rounding half of an atom every single time, I don't know. That's like saying that you're making $7.50 an hour at your snow cone stand, but every hour your boss just rounds down to $7. 40 hours a week, it's a lot of dollars in the long run. I don't know. So what we are going to equate this to is we're going to notice that 2.50, pretty dang close, to 2.5. And what you're going to run into in these circumstances, you're going to run into very familiar decimals. Decimals that you've seen since elementary school. I'm talking 0.33, 0.66, 0.5 as we see right here, maybe 0.25, right? Very familiar numbers. 0.33, of course, is 1/3. 0.66, of course, is 2/3. 0.25, of course, is 1/4. And 2.5 is equal to 2.5, as we just said right here. Well, what we're going to do in order to make all of our numbers whole numbers, as that's what the goal of our empirical formula is to have everything at a whole number in the end, is we are going to multiply every value by the denominator of the fraction that we have. So if this said 2.33, then we'd multiply everything by 3. If it said 2.66, we'd multiply everything by 3. If it was 2.25, we'd multiply everything by 4. And because it's 2.5, which is equal to 2.5, we're going to multiply everything by 2. And so now, we're going to like these numbers a whole lot more. I have 2 moles of nitrogen for every 5 moles of oxygen, which brings my final empirical formula, my answer, to N2O5. Next question reads, the empirical formula for a compound is CH2. Its molar mass is 294 grams per mole. What is the molecular formula for this mystery unknown compound? Remember, as we said before, the empirical formula does not have to match the molecular formula. And essentially what you have to understand is that whatever this original formula is, whatever the molecular formula was reduced by some whole number ratio. And so the big picture is we are going to find out how many of these fit into the molar mass. Now, they have to provide you this value. If they do not provide you the molar mass, you have no way of solving it. So you can find some consolation in knowing that you're always going to be given some extra piece of information here. They could ask you to calculate the empirical formula, but we just learned how to do that. But here in this problem, they actually gave us both. And so what we have to do is we need to find out how many of these fit into the 294 grams that they provided. Well, in order to do that, we need to find out how much one of these guys weighs. And so what we're going to do is we're going to look at the periodic table for the mass of carbon, which is 12.01, and add 2 hydrogens to it, which each have a mass of 1.01. And that gets a whopping total of 14.03 grams per mole in this empirical formula's mass, CH2. Well, now all we have to do is take the molar mass they provided, divided by that 14.03. As remember, we are finding out how many of these fit in this. And we should get a whole number. If you do not get a whole number or right around a whole number, then you know you did something wrong here. We get our answer to be 20.95, and I would say if you are any further away from that, maybe 20.94 or 20.93, you might want to consider that maybe you added up this number incorrectly, 14.03. But it is pretty dang close to 21, and so this tells you that the original formula was reduced by a ratio of 21 to give you the empirical formula of CH2. Now, this may be a weird way of writing this for some of you, right? But essentially what we're going to do is we're going to take our empirical formula and multiply by 21, which gives us our final answer, our molecular formula, C21H42. Now, our next question is actually going to tie empirical and molecular formula together. It's going to have us calculate both. May look a little daunting at first because there's more words than we've seen in the previous problems, but it's something we can't handle. We've been taught how to do each of these steps so far already. A compound contains 75.46% carbon, 4.43% hydrogen, and 20.11% oxygen by mass. It has a molar mass of 318.31 grams per mole. What is the molecular formula? So what we're going to have to do is the first part of this problem is we're going to have to determine the empirical formula, and then we're going to go from the empirical formula to the molecular formula. as we just did in the previous problem. So with the percentages they gave us, we can just immediately convert those to grams, because we are going to assume that we have 100 grams of whatever this mystery substance is, just like so. But as we've stated in all the previous problems, we can't compare grams of one element to grams of another element. So what we're going to do is we're going to divide by the molar masses of each of these elements. Carbon is 12.01, hydrogen is 1.01, and oxygen is 16. You can find each of those values on your periodic table, the molar masses. And so what we're going to get in our calculator once you plug those in is you're going to get 6.28 moles of carbon, 4.39 moles of hydrogen, and 1.26 moles of oxygen. Well, if you recall, what we do at this point right here is we've got moles, but it's not the most simplified way of looking at these moles, so we're going to divide them by the smallest amount of moles that we see present, and that's going to be 1.26. Then what you get in your calculator is 4.98 moles of carbon, 3.48 moles of hydrogen, and 1 mole of oxygen. The 1 is fine. The 4.98 can be rounded to 5, a whole number, but the 3.48 is right around 3.5, and that's going to be our issue here. And so because it is 3.5, we need to get rid of that fraction, essentially. And so if you will recall, 3.5 is essentially the same thing as 3.5. And so what we're going to do is we're going to multiply each of these numbers by the denominator here being 2. And then we get the true ratio, 10 moles of carbon, 7 moles of hydrogen, for every 2 moles of oxygen, which is going to give us our empirical formula, which was going to be C10H7O2 when it's all said and done. And we're going to need that for the next step. So now moving into the final steps of this problem, we are looking for the molecular formula of this compound, and we just determined that the empirical formula is C10H7O2, and the molar mass was actually provided to us in the problem. The molar mass is 318.31 grams per mole. Remember, if they do not provide the molar mass, then you cannot actually calculate it. And so all we need to do is we need to find out how many of these fit into this, because that is going to tell us the whole number ratio, that whatever this original substance's formula, the whole number ratio that that substance was reduced by. And so we need to find out how much this guy weighs. So 10 carbons, each with a mass of 12.01, plus 7 oxygens, each with a mass of 1.01, plus 2 oxygens, each with a mass of 16. Once again, you can find all of those values on the periodic table. And once you plug that into your calculator, you should get 159.17 grams per mole, give or take. And then what we need to do is we need to take our molar mass and divide it by the mass that we just calculated. And this is going to roughly give us a ratio of 2 that our original substance was simplified by. And so that tells us that we need to take our empirical formula and essentially multiply it by 2, which gives us our final answer, our molecular formula, C20H14O4. No problem. Easy peasy.
Quarantine log, day 17. I honestly thought that my dogs were talking back to me. What did you say?
The next topic of today's video is mole conversions, what you need to be able to do before you actually initiate stoichiometry. And so what you first need to understand is that the mole is the central unit of chemistry. You need to be able to go to the mole from whatever you're starting with. You need to be able to go from the mole to any of these options here. Mass, which you're almost exclusively going to see in grams. Volume, you're almost exclusively going to see in liters. And particles, you could see as atoms, molecules, or formula units, which is abbreviated FU, the only time you can get away with saying FU in chemistry. Either way, what are the conversions for each of these? Well, we need to understand the relationship between the mole, the mass, the mole, the volume, the mole, and the particles. And they each have their own number that we're going to consider here. Well, 1 mole is always equal to the molar mass. And so to go from mole to grams, you're simply going to relate the mole to the molar mass that you're going to find on the periodic table. And then to go from mole to volume, you're going to consider a constant. And that is, as long as you are at standard temperature and pressure, also known as STP, 1 mole is always going to occupy 22.4 liters, which is a really cool fact. 1 mole of any gas, no matter what that gas is, no matter what the shape of that gas is, the size of that gas, 1 mole of any gas, assuming that it is at standard temperature and pressure, will always occupy 22.4 liters of space. And then to go from mole to particles, remember that a mole is simply a term for a unit, just like a dozen or a score. Well, there's 12 eggs in a dozen. There's 20 soldiers in a score of men. Well, in a mole of anything, there's an Avogadro's number amount of stuff. And that is 6.022 times 10 to the 23rd. A really, really big number. 1 mole is equal to 6.022 times 10 to the 23rd. And it doesn't matter what you're talking about here, chemistry-wise, atoms, molecules, or formula units, it's all the same. It's always going to be occupied, or it's always going to have an Avogadro's number amount of stuff in 1 mole of whatever you're talking about. And so we're going to need this information and be able to relate these variables, these units, in our following problems. The first problem we see here is how many grams are in 3.30 moles of lithium? Well, if you wrote down our little chart that we just had a second ago, then you can see that the mole is smack in the middle. And if you're going from moles to grams, as we see in this problem, well, you can see that it only takes 1 line to get there. Moles to grams should only take 1 line if you're tracing your finger on that chart, which means this is only going to be a 1-step conversion. Now, I always write my train tracks, so to speak, like this, where I have where I'm starting at and where I'm ending with, a destination. So I consider these dimensional analysis train tracks like a GPS. I have a starting point, I have an end point. Oftentimes you have kids that don't put their start or their end point, and therefore they don't know when to stop. And so they just keep converting, and of course, inevitably get the question wrong. Well, all this is a giant fraction. And so what we can take advantage of here is that if moles is not in my answer, I want to become grams, well, then I need to get rid of moles. And because this is a giant fraction, what I can do to get rid of it is I can cancel it out by sending mole to the bottom here. Every teacher explains it a little different way. Some teachers say move diagonally, that sort of thing. I always like to think of whatever I'm starting with has to move to the bottom so long as that it doesn't match whatever I'm trying to end with. If moles is not my answer, then I got to get rid of it. So mole of lithium is going to go at the bottom. Well, we could go from the mole of a substance to the unit of any substance. And if you're looking at the chart from the beginning of this section of the video, then you saw that the mole was smack in the middle. Therefore, it's just going to be a 1-step problem. And so grams of lithium, moles of lithium. Well, on that chart, we wrote a few values there. And it said that 1 mole of lithium is going to equal the molar mass of that lithium. Well, where can you find the molar mass? Simply look at the periodic table. And the molar mass of lithium is 6.94 grams. And so, with this dimensional analysis setup here, we're going to take our starting value and we are going to multiply by the top and we are going to divide by the bottom. So in our calculator, we're going to do 3.30 times 6.94. We are dividing by 1, even though numerically it's not going to do anything to our answer. But in the end, we want to make sure that we are rounding appropriately to the proper sig figs here. We should get 22.9 grams of lithium. All right, the next mole conversion problem that we have here, number 8 on the worksheet if you are following along. How many liters are in 2.23 moles of oxygen gas? So we are starting with 2.23 moles of oxygen gas. Remember Brinkelhoff, so it's not just O, it is O2. We blow O's in the bathroom stalls. We breathe in O2s. And no, that was not me advocating for the blowing of O's. I am strongly against it. But I'm not oblivious to what's going on, the strawberry kiwi clouds. Hopefully, in the midst of this pandemic, you are withholding from all cloud blowing. Thank you for attending my TED Talk in the middle of this little lecture here. Anyways, 2.23 moles of O2, and we are converting to liters of O2. Once again, if you're looking at that chart from the beginning of this section of the video, it's simply a one-step conversion because moles is smack in the middle, and moles, it only takes one line to get to volume. So this is going to be a one-step conversion here. Well, moles is not in my answer, therefore I'm going to send it to the bottom. And liters is going to go on the top. Well, what are we going to put here? Well, what values do we put on that chart? In 1 mole of any gas, it's always going to occupy 22.4 liters, assuming that we are at standard temperature and pressure. And as far as we are concerned in this part of the course and this part of the unit, we are always going to be at standard temperature and pressure. We are not going to change that until we actually get to the gases unit of this chemistry course, which is later on down in the semester. Who knows if we'll actually be physically present in the building or if we'll be attending another one of these beautiful YouTube videos. Hope you're enjoying yourself so far. I know I am. I know I am. So all we do is plug and chug into our calculator, multiply the top, divide by the bottom, 2.23 times 22.4 divided by 1. Make sure we're rounding to the 3 sig figs that we started with. And so our final answer is 50.0 liters of O2. A little bit of give and take here as well, depending on where you are rounding in some of these problems, especially in terms of the molar mass. Here, there is no give or take. We started with a crisp value of 2.23. We used a constant 22.4 liters. So there should be no reason for us to get anything other than 50.0. In the previous problem, if you're using a different rounding for lithium, then you could get a slightly different answer. I'm talking 1/100 of a gram difference, 1/10 of a gram difference. I'm not talking 3, 4, 5 grams difference than the answer that we're actually getting here on the board in front. Next is how many molecules are in 1.56 moles of water. So we're still starting with moles, 1.56 moles of water. And we are converting to molecules. That H2O is hanging off the side of the screen. Don't worry, it is there, I promise. Well, if you will recall, molecules does fall into that category of particles. And so we are going to utilize a very, very large number known as Avogadro's number. Mole is going to go to the bottom. The reason why is because mole is not in my answer. I have molecules in my answer, therefore I have to send mole to the bottom. And in 1 mole of anything, there's 6.022 times 10 to the 23rd of that something. Molecules, I can spell. Once the top matches the unit that we are going for in the answer, we are ready to plug and chug into our calculator. 1.56 times Avogadro's number. We should get 9.39 times 10 to the 23rd molecules of water. Notice I'm not being lazy with any of my steps. I'm not just saying molecules, and I'm certainly not labeling my numbers here. I'm saying molecules of the substance that I'm talking with. When we get into stoichiometry, it gets a little more complicated. You're going from one substance to another substance. Therefore, you always want to be able to keep track of the substances that you're talking about. Not only that, if push comes to shove, if we're actually getting to test you on this material a little bit later on down the line, we can give you credit for every piece of work that you're showing. That being said, if you are not labeling your values, we don't know that you know what you're talking about. Therefore, don't be lazy. Label your stuff. Number 10 on your worksheet is how many atoms are in 26.50 grams of copper? Well, this problem is going to look a little different from the ones that we've done recently. Starting with grams of copper, and we're converting to atoms of copper. And if you're once again starting with that chart that we drew upon at the beginning of the mole conversions, you're going to see that going from mass to particles takes 2 steps, not 1. However, what do you have to run into in moving from mass to particles on that chart? You have to hit moles. The mole must be involved in every single step. And because I'm not starting or ending with moles, I know that I'm going to have to go through moles in the middle in order to get to my destination. And so this is actually going to be a 2-step conversion. So 26.50 grams of copper. Grams is not my answer, therefore I have to send it to the bottom in order to cancel it out. Well, just as I said a second ago, mole has to be involved in every single step of this dimensional analysis. So if the mole isn't down here, then he's got to be up here. Well, I don't know how many moles are in 26.50 grams. of copper, but I do know how to determine how many grams are in 1 mole of any substance. And that is if I look at the molar mass on the periodic table. And the molar mass of copper is 63.55 grams or so. 63.546 if you want to get picky. But then we are going to go from moles of copper to atoms of copper. Notice that our units do not match, so we are not finished yet. Mole has to go to the bottom in order to cancel it out. And atoms of copper must go to the top. Okay? Well, in 1 mole of anything, there's an Avogadro's number amount of stuff in it. 6.022 times 10 to the 23rd atoms of copper. And so what we are going to have to do here is actually 2 different calculations in our calculator. Make sure we are multiplying by the top and dividing by the bottom. So that would be 26.50 times 6.022 times 10 to the 23rd divided by 63.55 in your calculator. And in the end, we started with 4 sig figs, so you're going to want to round your answer to 4 sig figs. The answer I got in my calculator is 2.511 times 10 to the 23rd atoms of copper. Starting with 4 sig figs, ending with 4 sig figs. Mole conversions. Stoich is next.
Quarantine log, day 19. I haven't changed my shirt in 11 days. The days are starting to blend together. I've just sat in my bathroom for the last week or so, just hugging my toilet, crying. I've accepted the smell. Stay strong. We're going to get through this.
So now we get to the stoichiometry portion of this video. Some kids freak out about stoichiometry, but there's absolutely no reason because there's actually no new material here. And although you've been exposed a little bit to this in class before spring break, before all this craziness was happening, but a little bit of a refresher. What is the difference between stoichiometry and the conversions that we just did? Well, now the only thing that we're adding to it is an equation. Stoichiometry is essentially what you have to do in the kitchen, especially what you're doing nowadays. When you've got 1 taco shell, a banana, a nectarine, and a can of dog food, what can you make for dinner? Well, if I only have so much ingredients, how much product can I make with this amount of ingredients? And so there's lots of different metaphors that you could use, a lot of different analogies you could use to equate stoichiometry to what it actually is in the real world. But here in chemistry, we have to make calculations utilizing the chemical substances and the substances that we discuss in science. And so we're starting up with this reaction. Phosphorus, which maybe you didn't know, phosphorus actually travels in groups of 4, little gangs of phosphorus, plus oxygen gas, a diatomic element, makes diphosphorus pentoxide. Well, in every stoichiometry problem, if you do not first balance the equation, you have almost no chance of getting the correct answer. So we are first going to balance this equation before we even read what the calculation is that we're going to be asked to do. So I'm seeing that my phosphoruses are out of whack. Yes, the oxygens are out of whack, but we have to take care of that after. Phosphoruses are out of whack, so I'm going to put a 2 here. 2 times 5 is 10 oxygens, which means if I put a 5 here, now this guy is balanced. Okay? Our problem that we are starting off with, and this is starting off with 1-step stoichiometry, which means we only need 1 mathematical conversion in order to do that. Well, let's talk about what that conversion is going to be. That conversion is going to be utilizing the coefficients of the balanced chemical equation. What do these numbers actually mean when we put them out front of the substances? Well, when you put coefficients in, when you balance a chemical equation, you are establishing what is called the mole ratio. What this is now telling me is that for every 1 mole of phosphorus and 5 moles of oxygen gas, I can produce exactly 2 moles of diphosphorus pentoxide. That is the mole ratio. It is certainly not a gram ratio. Not for every 1 gram of phosphorus and 5 grams of oxygen am I making 2 grams of my product. That would not make any sense whatsoever. And so the question that we see here, number 11 on your worksheet, is how many moles of diphosphorus pentoxide can you produce from 3.33 moles of phosphorus? So I'm starting with my 3.33 moles. Yowza. Let's try that again. Try it all again. 3.33 moles of phosphorus. How many moles of diphosphorus pentoxide can I make? Okay. Well, this is going to be a 1-step problem, as I said. If we're going from moles of one substance to moles of another substance, that is always going to be a 1-step conversion. Well, moles of phosphorus is not my answer, so I'm going to send that guy to the bottom. and we are going to convert to moles of P2O5. Remember, mole is the central unit of chemistry. It is the only unit that we can be in when we are converting from one substance to another. I can't go from phosphorus to P2O5 unless I am first in moles as my unit. Well, where am I going to get these numbers here? With all the conversions we just did a second ago, we had very specific values, very specific places we were looking. Well, where's the only place that we can find these two different substances in close proximity? The balanced chemical equation. We utilize the coefficients, and it states that for every 1 mole of phosphorus, I can make 2 moles of diphosphorus pentoxide. So in my calculator, all I have to do is 3.33 times 2, and I will get my answer. And we want to make sure that we're rounding to the same amount of sig figs that we started with, so my answer is going to be 6.66 moles of my product. Next question is, how many moles of oxygen were reacted if you produce 12.88 moles of diphosphorus pentoxide? Well, they're telling us how much product we did produce, and so we're essentially going backwards. How much reactants did we use in order to produce this much product? Okay, so we're going to go from moles of P2O5 to moles of oxygen. Exact same setup as before, moles of one thing to moles of another thing. We are going to send moles of what we started with to the bottom, and moles of what we are looking for to the top. Where are we going to get these values? We're going to look to the balanced chemical equation. For every 2 moles of product, I'm going to use 5 moles of reactants in order to get there. So 12.88 times 5 divided by 2, and our answer that we get here, I've got a card for this one, fancy, right? 32.20 moles of oxygen gas. All right, all that is left on this video is 2-step stoichiometry and 3-step stoichiometry, which if you have a grasp of what stoich is, they look pretty much the same to you. A little bit of extra calculations in 3-step stoichiometry, but here we are with 2-step, and we're starting off with a new reaction. Lithium plus phosphorus makes lithium phosphide. And just as we did in the previous set of problems, we must first balance the chemical equation. Well, I see that my phosphoruses are out of whack, so I'm going to put a 4 here in order to fix that. And 4 times 3 is 12 lithiums, so I'm going to need a 12 here. Now we can actually look to our question. If I produced 2.12 moles of lithium phosphide, how many grams of lithium were reacted? So always write down what you're starting with. And always write down where we are going. We're going to grams of lithium, like so. Well, going from moles of one thing to grams of another is actually 2 steps. But what we are going to do is we're going to go from moles of what we are starting with to moles of the substance that we want to end with, and then the final step is going to look a whole lot similar to the previous section of problems we just did with the mole conversions. So first, moles of lithium phosphide must first go to the bottom, as that is not in my answer, therefore I don't want to see it. I got to get rid of it. And I have to convert to moles of the substance that I want to end with. I can only go from one substance to another if I am in moles. It is the central unit, the universal language of chemistry. Well, where am I going to get the values here? The balanced chemical equation. For every 4 moles of lithium phosphide, there are 12 moles of lithium. As you can see, moles does not match grams. Therefore, we are not done with our math yet. Moles must go to the bottom, and grams is going to go on the top. Well, where am I going to go from moles to grams? Well, I am going to rely on the fact that I know how many grams are in 1 mole of anything, and I can look to the periodic table for that. And in 1 mole of lithium, there are exactly 6.94 grams. So when we multiply by the top and divide by the bottom, that's 2.12 times 12 times 6.94 divided by 4. It does not matter what order you do those operations in, you're going to get an answer of 44.1 grams of lithium. Let me move that down here for you. Notice we started with 3 sig figs. We want to end with 3 significant figures as well. Our final problem for the 2-step stoich section is how many molecules of phosphorus are required to completely react with 5.00 moles of lithium. Write down what we're starting with. And we are ending with molecules of phosphorus. Remember, phosphorus here in this equation is not just P, it is P4, as that is how it naturally exists. Moles of lithium must first go to the bottom, as it is not in my answer, therefore I got to get rid of it. And we are going to convert to moles of the substance that we are concerned with, which is phosphorus here. You're going to look to your balanced chemical equation in order to get to the numbers here. There are 12 moles of lithium for every 1 mole of phosphorus, as we can see in our coefficients. Well, mole does not equal molecules, and if you're not labeling every step, some kids do make that mistake. Mole does not equal molecules, so there is still one more step for us to do. In 1 mole of anything, there's an Avogadro's number amount of stuff in that mole. We squeeze in molecules here. Hopefully you can read that. And so now in my calculator, I notice that molecules matches molecules, so we are done with our conversions. 5 divided by 12 times Avogadro's number. What I got in my calculator is 2.51 times 10 to the 23rd molecules of P4. Like so. 2-step. It's like 1 step, but 2. 3-step coming up. All right, 3-step stoichiometry. Of course, we are going to start with something that is not moles and end with something that is not moles. As it stands for 1 step, you are starting and ending with moles. For 2-step stoich, you are starting or ending with moles. And for 3-step, you are neither starting nor finishing with moles. But you have to use the moles to get to your destination. And that's the $1 million fact here. And so we're going to have our reaction here. Sodium plus gold 3 chloride. This is a U. Let's try again. My students always make fun of my U's. I don't see the confusion. I really don't. Stop bullying in 2020. And as always, we have to balance our chemical equation. We've got 3 chlorines on the left, only 1 on the right, so let's fix that. And now we've got 3 sodiums on the right and only 1 on the left, so we put 3 there to balance it. If we don't do that balancing step, we are greatly reducing our chances of getting the question correct in the end. The question that we're starting off with, number 15, how many grams of sodium are required to produce 100.0 grams of gold? What a lucrative gold producing business this guy has started up. Simple chemical reaction to produce pure gold. Amazing. We're starting with grams and ending with grams, a 3-step conversion. Well, we can't go from grams of one substance to grams of another substance. That's like comparing potatoes to Granny Smith apples. Very different flavor profiles if you know anything about the culinary industry. And so the only thing that they do have in common is that we can convert them to moles, and then they're speaking the same language. Okay? So we're going to convert grams of gold to moles of gold, and then proceed towards a destination. And so grams must be canceled out, because it is not in my answer. So grams of gold goes to the bottom. And just as we said a little bit further back in the video, the mole must be involved in every single step of every single stoic problem. Well, if he's not here, then he must be on the top. And in 1 mole of anything, that is going to equal the molar mass of that substance. Where can you find the molar mass? The periodic table. 196.97 grams in a mole of gold. From there, we're going to go from moles of gold, not straight to grams of sodium. We cannot do that. We must first convert to moles of sodium. So mole of gold is going to go to the bottom, and moles of sodium on the top. Well, where are you going to get the numbers to fill in the blanks here? When you're relating moles of one substance to moles of another substance, we're going to look at the coefficients of the balanced chemical equation. For every 3 moles of sodium, there's 1 mole of gold. We're almost there. Moles of sodium, not quite grams of sodium, so we're going to do 1 more step here. In 1 mole of anything, it's the exact opposite of this step over here. In 1 mole of sodium, it is going to equal the molar mass of that substance, 22.99 grams of sodium. So we're going to multiply across the top. We're going to divide across the bottom. 100.0 times 3 times 22.99 divided by the mass of gold. And we're going to get our answer as 35.02 grams of sodium. Notice we started with 4 sig figs. We also ended with 4 sig. And our final example on this video, number 16 on the worksheet. How many formula units of sodium chloride are produced if 64.5 grams of gold 3 chloride are reacted? We're going from grams of one substance to formula units of another substance, essentially particles of another substance. So we're not starting or ending with moles, which tells you this is also a 3-step conversion problem. So we're starting with 64.5 grams of gold 3 chloride, AuCl3. I promise that's what that says. And we are converting to formula units. Remember, the only time you can get away with saying Fu in chemistry, Fu of sodium chloride, NaCl. Okay. Grams of gold 3 chloride is not in my answer, so I'm going to send that to the bottom. And if the mole is not on the bottom, well, then the mole must certainly be on the top, as the mole must be involved in every single step. Well, where are you going to find the molar mass of gold 3 chloride? You have to do a little bit of extra work on this one. You have to actually find out what the molar mass of gold 3 chloride is. So we're going to have to add all this up. Gold is 196.96 or 97, whatever floats your boat. And there's 3 chlorines. The molar mass of chlorine is 35.45 apiece. I've done the math already for you. You should get a molar mass of 303.32 grams per mole. Give or take a few hundredths of a gram. If you're using a different periodic table, it's got different molar mass values, well then obviously you're going to get a slightly different molar mass here. But it shouldn't be too far off from what we've got here. Okay? And that is going to equal the mass of 1 mole of whatever the substance is that you're talking about. Now we're going to move from the substance that we started with to the substance that we want to end with, which is sodium chloride. Mole of AuCl3 is going to go to the bottom. And moles of NaCl on the top. Where do we look? We look to the coefficients of the balanced chemical equation. For every 1 mole of gold 3 chloride, we are producing 3 moles of salt. Not quite at our destination yet. And pardon me, I usually have an extra block at the end, but we're running out of space here. So, final step. For every 1 mole of NaCl, there are going to be exactly an Avogadro's number amount of stuff in it. Remember, formula unit qualifies in that particle category. It's just like solving for atoms or molecules, same sort of thing. And so we're going to multiply by Avogadro's number in the end. It doesn't matter what order you do these operations in, you should still get the same answer so long as you are plugging into your calculator correctly. The number that you're starting with, divided by any number that's on the bottom, and multiplied by any number on the top, we get our answer to be 3.84 times 10 to the 23rd formula units of NaCl.
Quarantine log, day 23. Today was all right. I learned some chemistry. Bad news is it was Friday, and I didn't hear a funny joke. Corona.